Welcome back. This module we're talking about interpolation and spatial statistics. Last time I talked about a couple of methods, natural neighbor and spline interpolation. The other two methods I've covered are trend and inverse distance weighted, sometimes known as IDW. The other interpolation method we're going to cover in this class is called kriging. But kriging takes into account some statistical concepts. So before I talk about kriging, I need to kind of get you used to thinking about statistics again. Okay, so this video is about traditional descriptive statistics, which means we're going to talk about values that don't necessarily have locations associated with them. So you can imagine that we have, for an example, let's say we have all of the 20-year-olds in the world, and we would like to know about the weight of all of the 20-year-olds in the world. So that would be considered the population, all the 20-year-olds in the world. And we know we can't measure the weight of all the 20-year-olds, so we're going to measure the weight of a subset of 20-year-olds, and we're going to call that a sample. And with descriptive statistics, if the sample is adequate, we will be able to develop some measures that will allow us to do inferential statistics, which would infer properties of the population based upon the properties of the sample. But this video is going to be just about descriptive statistics. So we have all these 20-year-olds in the world. We do a sample of the 20-year-olds and we weigh them all. And so that is our sample. And that sample will have what's called a distribution. And a distribution will have two kind of basic measures of where the middle of the distribution is, and that's called central tendency, and another one that's measures of dispersion, which is how those values, how the weights spread out from that central tendency. Okay? So when we do this sampling, we get these values, and we can plot the values up into, remember, what's called a histogram, or we can consider that the values fall into what's called a statistical distribution. And there are a whole bunch of distributions. Here's an example that shows a bunch of continuous distributions. So this is for continuous phenomena as opposed to discrete or single-valued phenomena. And depending upon the population that you're sampling, that population might behave according to one of these distributions better than other distributions. So you all probably remember the normal distribution. This is that traditional bell-shaped curve, and if when you plot up all the values in your sample, your curve kind of looks like that curve, then you might say, well, this is kind of like a normal distribution. But that's not the only kind of distribution that's out there. Of course, from that thing on the left you can see there's a whole bunch of different distributions. Sometimes you'll see a distribution that is skewed to the left, which means it has a tail that kind of drags out to the left. And the way I remember skewing to the left is it's pointing to the negative side of what would be a number line, so that's going to have a negative skew. You can have a distribution that skews to the right, and you can imagine that that tail is pointing out to the positive side of the number line, so that's going to have a positive skew. You might think of something like, let's say, precipitation, where most of the time when it rains, it doesn't rain very much, so this might be a low value of precipitation. But sometimes there's a lot of rain that comes down at one time, so you have this tail that pulls way out to the right. That might be skewed right. Sometimes you might have a bimodal distribution, and you can imagine in this example where we have the weight of 20-year-olds, if there are equal numbers of males and females in our sample, then the weight of females might have a central tendency kind of on the lower side of a weight, and the weight of males might have a central tendency on the higher side. I don't know if that's true, but if that were the case, then that might be a bimodal distribution. A uniform distribution is a distribution where basically the chances of getting any value along your line are equal. And for continuous distributions, I'm not sure that I have a good example for that, but for discrete distributions you can think of rolling of a die. And so the chances of getting a 1, a 2, a 3, a 4, a 5, or a 6 are all equal, so that would have a uniform distribution. So once you take the sample, get all the values, plot them up, you can see that it's going to follow some type of distribution. So how do we kind of measure what's going on with the distribution. So again, there's central tendency and there's dispersion. So the three measures of central tendency are the mode, the median, and the mean. So all these should mean something to you. I'm sure you've had this before, so this is just review. What the heck is the mode? That's the most common value in the data set. So if we measure 100 people and 53 people weigh 143 pounds and nowhere near that many people weighs any of the other values, then the mode is 153 or 43, whatever I said. Okay, the median is the central value. You order all the values, and the value at which there are the same number of values above and below that value is the median. So you rank them all, pick the middle, and that's the median. Problem is that if you have an even number of values, there is no even value on your ranked set of values, so you have to take the average of the two that are one in the other side of the average, of the middle, I mean. The mean is the average value. Here's the equation. You add up all the values and you divide it by the number of values. That gives you the mean. So those are the three measures of central tendency. And in a normal distribution, the mean, the median, and the mode are all going to line right up in the middle of the distribution. And you can imagine the other distributions, how the mean and the median and the mode might scatter apart from each other. And so you can kind of get an idea of what kind of distribution it is by looking at those values and seeing how they compare. You need to remember that thing I talked about earlier on, the ecological fallacy, and that's where people seem to think about when something is presented as an average over a larger area, that everything inside of that area has that average value. So you can imagine average income in the state of Idaho, that's a single number. It's computed using this equation. But you can imagine that there are a lot of higher incomes and lower incomes that get added up and averaged out over the long run, and that's the ecological fallacy. Okay, what are the measures of dispersion that we're going to think about? Well, the first one's called the variance, and then we have something called the standard deviation, which is the square root of the variance. We have the skewness, which is going to tell us whether the distribution leans one way or another. And we have the kurtosis, which is going to tell us something about the tails, the outliers of the distribution. What's the variance? Here's the equation for the variance. You take each value and you subtract the mean from that value. You square that quantity, add it up for all of the values, divide by n minus 1, and that's called the variance, which is symbolized s squared. So you can imagine that if a number is less than the mean, I'm going to have a negative number in here, but I'm going to square it, which means it's going to be positive. If this number is greater than the mean, I'm going to have a positive number, square it, it's going to be positive. So all of these terms are going to be positive numbers, so the variance is always going to be a positive number. Standard deviation is basically the square root of the variance, okay? And that's kind of the average variance. You can think of it as the average variance. So if values are a long way from the mean, you're going to have a high variance and a higher standard deviation, which means your distribution is going to be kind of spread out as opposed to compacted in close to the mean, which would be the case when most of your values were real close to the mean. So high values, more dispersion, spread out distribution. For normal distributions, you can take a step further and say that 68% of all the values are within plus or minus 1 standard deviation of the mean. 95% are within plus or minus 2 standard deviations, and 99.7% are within plus or minus 3 standard deviations. So if you know the type of distribution, and it's a normal distribution, and you can compute the standard deviation, you're going to be able to infer that there are a certain percentage of your values of the population that will fall within these ranges. Okay, what's the skewness? Skewness is the third moment here, and so what we're doing is we're taking each value minus the mean, just like we did in the variance and standard deviation, but instead of squaring it for the variance, we're going to cube it. So you can imagine if a value is less than the mean, this is going to be negative. Negative number cubed is going to be a negative number. If this is greater than the mean, it'll be positive. You cube a positive, you get a positive. So things on one side of the mean will be canceled out by things on the other side of the mean. So your skewness in a perfectly symmetrical distribution will be 0, because everything will balance out. If things are skewed to the left there are a lot of things, a relative lot of things to the left of the mean, which means your distribution will have that tail that points to the left, and your values will be less than the mean, which means your skewness will be less than 0. So that measures asymmetry in your distribution. If things are symmetric, like a normal distribution, skewness is 0. If it's less than 0, that means the tail points to the left, and it's called negative skew. Greater than 0, the tail points to the right, positive skew. Okay, kurtosis, getting to be fancy terminology here. We're going to go up one order in what's called our moment. This is the 4th order, and you take anything to the 4th power, it's going to be positive. So we know that kurtosis will be a positive number. The term excess kurtosis subtracts 3 from this equation here, and the reason it does that is excess kurtosis that will then be 0 if you have a normal distribution. So it's a way of normalizing things to a normal distribution, so you'll be able to compare things to a normal distribution. And what this will end up doing is it will kind of give more influence, since it's the 4th power, to these values that are a long way from the mean, and that means the higher the value, the thicker your tails, which means there are more values out in this range here. So kurtosis measures how thick the tails are. Excess kurtosis is going to measure how thick the tails are compared to a normal distribution. If excess kurtosis is 0, then it's approximating a normal distribution, and we'll be able to make a lot of those assumptions that we did before. If it's less than 0, we have thin tails. Okay? Thin tails means there's not a lot in terms of number of values out at the extremes of the distribution, which means there aren't so many outliers. So negative kurtosis, fewer outliers. If you have positive kurtosis, you're going to have more outliers. So this is a valuable measure to give you an idea of how your data compare in terms of dispersion to the mean, and how many outliers or percentage of outliers that you might need to look at closely and take out of your sample if the outliers for one reason or another should not have been contained in your sample. Okay, so that was basic descriptive statistics. Traditional descriptive statistics doesn't have anything to do with the location of these values that you measured. Next time I'm going to talk about the other type of interpolation that we're going to consider in this class, and that's called kriging. Kriging is really complicated, and it utilizes some concepts that are statistical, so we'll get into that in the next video.